Hello everybody. In the last session, we were discussing about the DC motor. We discussed about the various characteristics, the various types of excitations, the series, the shunt, the compound excitation, and we studied the characteristics of the shunt and the series motor in some detail. Today we shall continue from there and complete our discussion of the DC motor by studying the compound motors and the other issues like modeling of the DC motor. Now, we discussed about the shunt and the series motor, and there were few unique features which were representative of these two motors, that is the shunt and the series motor. Now, if you look at the shunt motor, in the case of the shunt motor, the generated torque Tg is proportional to the flux, field or the excitation into Ia. In the case of the series motor, the generated torque Tg is proportional to the flux into Ia, but the flux itself is proportional to Ia, and therefore, you have it proportional to Ia square. In the case of the shunt motor, let us say in both the cases Ra is equal to Ra is approximately equal to 0, Ra is approximately equal to 0. The back EMF will be equal to the applied armature voltage, and which will be equal to some proportionality constant into phi into omega. Now, as this is a constant, we saw that if we decrease the flux, the speed is going to increase, or if we increase the flux, the speed is going to decrease, because this is a constant and these two are inversely proportional to each other to maintain this constant. So, when under no load conditions, if we suddenly remove the excitation winding, or if the excitation winding gets cut, then phi becomes 0, the motor speed will increase to a very huge value, and the bearings may get damaged. So, there may be mechanical damage to the motor, and such a situation is called a runaway of the motor. In the case of the series motor, the back EMF Eb is proportional to phi and omega, and as phi is proportional to Ia, is proportional to Ia and omega. If Ia is 0, that is at low speeds, if Ia is 0, when at the time when the shaft is not rotating, the Eb is 0. So, even if there is an Ia and the shaft is rotating, is not rotating, that is omega is equal to 0, Eb is 0. Under no load conditions, when let us say Ia is close to 0, then also Eb is equal to 0. Now, let us say you apply the full applied voltage. The full applied voltage is applied, the shaft is not rotating, then the Ia is going to be very high, the torque generated is going to be Ia square, it is going to be a huge torque, and under no load conditions the speed may accelerate very fast, and again it may result in this runaway in the case of the series motor and result in mechanical damage. So, even the series motor, because at omega is equal to close to 0 speed, there is no back EMF, the Ia will be very large, and that large IA is also going to result in a large field, because the field current is the same as the IA, and therefore, as a consequence the speed will quickly pick up and try to run away. But under loaded conditions, the torque will develop and then settle down at the operating point depending upon the load torque requirement. So, the runaway situation can occur in both the cases, and the runaway here is the case when field winding gets cut. In this case, under no load, when you switch on the armature voltage EA, under such conditions it can run away. So, here the runaway condition would be field suddenly goes to 0, and here runaway condition would be, and of course no load. No load, startup of the motor, where you apply the EA. So, the IA starts increasing, and then that will give you a torque which is proportional to IA square, and then the speed picks up very fast. Now, in the case of the series motor, as the torque is proportional to IA, and during the startup the back EMF is almost close to 0, IA will be large, and therefore torque, as it is proportional to IA square, the generated torque, it has very high low speed torque in the case of the series motor, whereas in the shunt motor the torque is limited because it is just proportional to IA, and it is limited to IA, which is the rated value. If IA is having a per unit value of 1, that is 100%, torque will be having per unit value of 1. But in the case of TG, which is IA square, it is square times the rated value. So, therefore, you have a TG which is, for example, if I am having IA is equal to 10 amps rated for both the cases, TG will be proportional to 10 amps, whereas TG will be proportional to 100 amps for a 10 amps rated. This makes a torque which will be much higher than the shunt motor torque for the same armature winding rating of the currents. So, this makes series motor special in some kind of application where you need very huge torques, especially at low speeds. Now, some such applications would be like in traction, in electric traction. A series motor will be able to generate a very high torque in starting in overcoming the initial inertia, or in the cases like cranes, where it may need huge torques in lifting a particular load. Now, these are applications where a series motor would be ideal. Now, a compound motor. A compound motor is a combination of these two. That is, you have the motor, we have the brush. The brush is connected to the electrical wires. Let us say we have an RA, the armature winding resistance. Now, the brushes are connected to the terminals of the motor as shown like that. So, across the terminals of the motor we apply EA, and there are two windings. One will be the winding, we will call it as the shunt winding, and then let us say there is another winding, let us call it as the series winding. So, the shunt winding and the series winding are connected in a fashion as shown, that is, we have the shunt winding which is connected across the applied source, and of course, we need to have a RF here, R shunt. Now, the series winding will be connected in series as shown, where the armature current flows through the series excitation winding. So, you have a phi series and a phi shunt. So, the series winding, the shunt flux will be the dominating flux in most of the cases. So, you will have the resultant flux which is the shunt flux plus or minus the series flux. That is the shunt flux, meaning the flux generated by the shunt winding plus or minus the flux generated by the series winding. If it is aiding, then we say it is a cumulative compound. Cumulative compound. So, in a cumulative compound motor, the flux is the shunt winding flux plus the series winding flux. They aid each other, they add up, and then you have a larger flux. And the differential compound, the flux, resultant flux will be the shunt winding flux minus the series winding flux. So, the resultant flux is going to be lesser in amplitude. So, in a cumulative component, at initial startup condition, omega is equal to 0, there is no back EMF, IA has not started, but there is still IF, that is I shunt, which is going through the shunt winding. So, there is a shunt excitation which is there. So, phi shunt is there, is present inside the machine, and IA is beginning to grow. So, during initial conditions, the motor will act like a shunt motor. Then once the gradually the motor is picking up speed, you have IA also flowing because of the load. Because of the load, we have the series field contribution also. So, under no load conditions, IA is going to be negligibly small. So, even under those conditions, you will have the flux contributed by the series much smaller than the shunt field flux, and therefore, under no load conditions, it will act like a shunt machine. And therefore, under no load startup condition, where the series motor would run away, in this case under no load startup condition, it would be like a shunt machine, and therefore, there won't be the possibility of runaway under such conditions. In the case of the cumulative component, under full rated load, the series field flux plus the flux due to the shunt, they add up and they will reach the rated flux. Now, the under load conditions, because IA is going to be large, the flux is going to be higher than under no load conditions, where the series field flux is going to be less significant. So, the flux in the machine is going to increase from, let us say, phi shunt value to phi shunt plus phi series value as the load increases from no load to full load. So, as the flux increases, you saw that the back EMF is connected across the armature winding, and if you say the back EMF is constant for a given speed, then as the flux increases, the speed will reduce. So, which means that as the load is changed from no load to full load, flux is increasing and the speed will reduce. And in the case of the differentially compound, as the load is increased from no load to full load, the field starts from phi shunt value and starts decreasing. So, as the flux decreases, the speed will increase to maintain the back EMF constant. This means that in the differential component there could arise some instability due to increasing speed, and that could cause some runaway issues. So, normally the compound motor is not wound for differential purpose. It is normally wound as a cumulative compound motor. Let us understand, consolidate with a couple of examples, one on the shunt motor. Now, let us say we have a shunt motor. We have a shunt motor. Now, the shunt motor is rotating at 1500 RPM, and it has a 120 volts DC as our EA applied to the terminals of the motor. Now, IA is 51 amps and our shunt or RF or field winding is 120 ohms. RA is given as 0.1 ohms. Okay. Given this, let us calculate IA let us calculate the EB and let us calculate the mechanical power developed by the motor. Let us do these three things. So, let me have a copy of this so that we shift pages, we could look back at that. Okay. Now, we know that the schematic is like this. This is a shunt field. We have RA, we have the field winding, the brushes, the mechanical load is connected in this fashion, terminals of the motor. We have EA which is applied here, we have IF flowing through this, there is also RF, there is IA which is flowing through this, and let me just make a modification. What we take from the current here is the, let us say, the source current is 51 amps. Okay, instead of saying IA is 51 amps, let me take it as the source current as 51 amps. So now what we have is, this is 51 amps. We have 120 volts, and this is rotating at 1500 RPM. Okay. Now RA is 0.1 ohms and RF is 120 ohms. So we have these things which are. And now let us calculate first IA. Now IF is known, easy to calculate, which is 120 volts by 120 ohms, which is equal to 1 amps. So 1 amps flows through IA, 51 amps is coming from the source. So IA is equal to 51 amps minus IF, which is equal to 50 amps, because IF is 1 amp. Now what is EB? Now EB is the back EMF, which is across the brushes, that is EB. It is EA minus IA-RA drop. EA minus IA-RA drop, which is 120 minus 50 amps into 0.1 ohms, which is 115 volts. This is the third. Now the final point in this problem is that we need to find the mechanical power which is given to the load. So if you look at what is the power that we actually deliver to the load, what we get here is EA, IA square RA drop goes off, and what is given is ultimately the power which is. So the power, let us first find what is the power which is drawn from the source, P source or PA. So PA will be EA into 51 amps, which is 120 volts into 51 amps, which is equal to 6120 watts. And what is the power absorbed in the armature? The power absorbed in the armature P armature will be EB into IA watts. So EB into IA watts is nothing but this voltage which we calculated, which is 115 volts, into this current which is 50 amps, which is 0, 5750 watts. So, this is the power that is delivered to the armature and given as, which will appear as the mechanical power that can be developed by the motor. So, this is your final the third point in the question which can be answered. So, let us take up just one more example on the series motor. So, let us say we have a series motor which is rated for 15 HP, 240 volts, 1780 RPM and rated current of 54 amps. Now, let us calculate the current and speed when load torque is 224 Newton meter. Is 24 Newton meter. Let us further say that there is a torque speed curve, there is a torque speed and torque current curve which is given for the series motor, which looks like this. This is torque, and on the x axis you have the speed n and also the IA, both these are. So, the torque speed curve, this is torque versus speed. So, as the speed is increasing, the torque is reducing, and at very low speeds the torque is going to be very high, IA square, and there is torque versus IA. Let us, so when IA is equal to 0 is like that, and then it is taking a square form because torque is proportional to IA square. So, it goes in this fashion. Okay. And let us say this is our rated load. So, this would be the rated load, and this would correspond to our per unit 1. So, if we say these are all in per unit values, this is also in per unit values, and this would be 1.0, 1.0. So, at rated current, 100% current, there is a 100% torque. So, this is the condition, that is this is the graph which is also given to us. So, now let us calculate the various things asked. Now, what is the power? The power or the base power, we will call it as PB, which is 15 HP, and let us convert it into kilowatts, which is 15 into 746, which will be 11,190 watts. Okay. This is the conversion that we have assumed for the conversion from HP to watts. 746 watts is 1 HP. Then the base speed is 1780 RPM, and the base current is 54 amps given. Now, the base torque is given by the relation which we worked out before, which is, let us say, power, base power divided by speed in radians, but we have the speed in RPM, n RPM into 2 pi by 60 would give in radians, which will be 60 into 11,190 watts divided by 2 pi into 1780 RPM, which is 60 Newton meter. Newton meter. This is the base, TB base. Now, the torque, load torque is 24 Newton meter. This means per unit value wise, per unit would be 24 by 60, which is 0.4 pu. So, all should be calculated at 0.4 per unit value. So, when we go back to the characteristic, let us say if this is 1 and this is, and somewhere here is our 0.4 per unit. So, at that we have speed which is 1.4 per unit, let us say, as given. So, the speed now would be the speed at 24 Newton meter torque is equal to 1.4 into 780. That is, this is obtained from torque versus speed characteristic. Now, this is equal to 2492 RPM. Now, the current I at, that is IA at 24 Newton meter will be whatever the current in per unit obtained from torque versus IA characteristic into I base. So, which will be, so going back to the characteristic here, you will see that it cuts the torque versus IA curve, the torque versus IA curve around 0.6, let us say 0.6 per unit. So, this would be 0.6 into 54 is equal to around 32.4 amps. So, this would be the IA and the speed at a torque of 24 Newton meter for a characteristics as given like this for this particular machine. So, this is how one goes about calculating for this one. So, now we have one more major issue in the motor, and that is how to stop the motor, that is braking. How do we stop the motor? So, the braking is accomplished by four methods, can be accomplished by 4 important methods, 1, 2, 3, 4. First one is the simplest, we call it as coasting, let us say. The second one, by applying mechanical friction. By applying the mechanical friction on the mechanical side. The third one, on the electrical side, you are applying a load which is called the dynamic braking. And the fourth one is called plugging. These are the 4 methods in which one may try to stop the motor. So, if you look at the schematic of the motor system, let us say we have the DC motor, brushes, the brushes are connected to in this fashion. Let me now make a small modification the way we normally draw the schematic. Now, so I am going to have these 3 positions here. Now, here I am going to let me take another color. So, here I am going to put our EA, okay, EA. Now, there is of course the field winding which is also going to be connected to EA. So, this is RF and there is going to be a IF field. So, this is going to generate your phi. Okay. Now, this is your IA, armature current. Now, I am going to have a double pole, double throw switch. This is a double pole, double throw switch. Let us give some names. Let us say A, B, C, D, E, F. EF. Okay. Now, what we propose to do, this is the DC motor. Let us have the back EMF EB here, then we are going to connect the shaft to the load. So, this is the system that is right now existing. I will make a copy of this for future. Copy. Okay. Now, the motor is rotating, which means we have a generated torque and it is rotating at some speed omega. Now, we want to bring it to a stop. So, what do? Now, when the motor is rotating, that is, let me call it as motoring. So, when it is motoring, A, C, B, D are connected. A and C are connected, B and D are connected. That is, here we put this double pole, double throw switch to positions C and D. So, A and C are connected, B and D are connected. So, which means the armature voltage is applied to the brushes of the motor. So, this will cause IA to flow and therefore, motoring will happen and then there will be generated torque and therefore, the speed. Now, if we open this switch, that is disconnecting this switch such that A and C are open, B and D are open. Under such condition, there is no IA flowing, which means IA is equal to 0. IA is equal to 0 means generated torque, that is, if A, C, B, D are open, IA is equal to 0, force to 0. What happens to TG? TG being proportional to phi IA, TG also becomes 0. There is no generated torque, but there will be inertia on the mechanical side which will make it to continue to move. Like if you are traveling in an automobile, if you switch off the engine, it will still continue to move because of the momentum, because of the inertia which is stored in the mass of the vehicle. So, we just allow it to gradually die down, there is no torque applied. So, on its own, because of the frictions associated in the bearings and so on and so forth, the shaft will coast and gradually come to 0. Now, that may take quite a long time depending upon the amount of inertia which is there on the shaft. Now, that is called coasting mode. In the coasting mode, we are not doing anything, there is no extra circuitry, we are just opening out the armature such that the IA is 0, the generated torque is 0 and it will gradually come to 0. What will come to 0? The mechanical speed, the omega will gradually come to 0. Now, if the inertia of the mechanical system, whatever is connected as a mechanical load is very high, then it can take quite a long time for it to coast down to 0. So, what can be done? We could take the second method, which is applying mechanical friction. So, let us say to this system which we have here, let us apply brakes like in a vehicle. So, let us say at this point I am going to put something here and let me call that one as brake shoe. Now, I apply a force F to the brake shoe. So, which means the mechanical shaft is rotating and you are going to apply force onto the brake shoe and the brake shoe is going to hold on to the shaft, and then due to the friction between the brake shoe and the rotating shaft, the mechanical system is going to come to a halt, which means the mechanical energy which is stored in the inertia is going to get dissipated as heat in the friction. So, therefore, you have the loss loss of the energy through the heat developed because of the mechanical resistance of the heat in the friction. Now, this is called mechanical braking. Now, we could also try to break it not only in the mechanical domain, because we say that there is an electrical domain and the mechanical domain, and we can move through any of the domain because energy is domain invariant. You can apply the brake or try to remove the energy which is there in the inertia on the mechanical domain by dissipating in a resistor in the electrical domain. That is also possible. That is called dynamic braking. So, in the dynamic braking, what we do, the inertia, the energy stored in the inertia of the mechanical domain is going to get reflected as EB. It is a generator. Now, that EB, we will try to remove it by connecting a resistor here, let us say. Now, I will say RB. So, when it is motoring, the switch here is connected to C and D. So, which means AC is short, BD is short, it is motoring, IA is flowing. Now, during braking, we open the switch and connect it to E and F, which means A and E is short, B and F is short, which means now the whole system is acting like a generator. The inertia is rotating the shaft, there is a generated voltage EB, which is going to be seen as a voltage across the terminals of the motor here, and then applied to a load RB. So, there is a current which is going to flow in the reverse direction, IA, or if the current is already flowing in IA, that is going to decay pretty rapidly because that gets dissipated in RB as IA square RB. So, therefore, the energy stored in the inertia, instead of being dissipated in the mechanical friction here, is going to be dissipated as electrical heat in the resistor or the braking resistor RB shown here, due to the armature current now flowing through the resistor. This will bring down the speed pretty quickly, just like in a mechanical brake. Now, this kind of braking is called dynamic braking. The value of RB here is chosen equal probably to the rated current, or sometimes even to twice the rated current, depending upon how quick you want to have the braking effect. If it is twice the rated, if it is chosen as EB by 2IA is the value that you need to calculate for RB, then it can handle twice the rated current for that same EB which is produced due for that particular speed. The RB value is much lower, and therefore, more IA flows through RB and then gets dissipated much faster, because higher the value of IA means IA square RB is going to be much higher, and therefore, the amount of energy that is drawn in a unit time will be more, and therefore, the speed at which it will reduce and come to 0 will be much faster. Now, in the fourth case, called plugging, what is done is we shall connect another source like this. Now, I will call this one as EP or E plugging or EB. No, EB is for the back EMF, EP is for plugging. So, now what is done is when A and C are connected, A and C are connected, B and D are connected, then it is motoring. Under such conditions, IA is equal to EA minus EB by RA. Now, when we want to stop, we open this double pole double throw switch and then connect it to E and F. So, while braking, A and E are connected, B and F are connected. This is braking. So, under these conditions, what is IA? Now, you see the polarity here. We have applied a reverse polarity here as compared to EA. So, this would be in line with the generated back EMF polarity. So, IA would be EP plus EB by RA, and that is in the reverse direction. Immediately it is going to change the direction. You are going to have a reverse current flowing, but it will be of pretty high value because RA is going to be small, whereas here it was the difference in voltage between the armature voltage and EB. Here it is EP plus EB, and EB can be any value up to EA, and therefore, a very huge armature current is going to flow during this braking time when you are putting the double pole double throw switch to EF position, and this will try to make the motor, it is like applying the armature voltage in reverse, which will try to make the motor rotate in reverse, which means it immediately has to come to a stop and then starts rotating in reverse. So, when it comes to a stop, then you just remove the double pole double throw switch such that IA becomes 0. Now, this can be pretty fast, and this is called plugging. The value of IA can be very high, something like 50 to 100 times the rated current. So, the armature windings may or may not be able to handle that. So, it has to be properly designed. Under such cases, one will have to put a series resistance. One will have to put a series resistance RP such that IA becomes, during braking or plugging, EP plus EB by RP plus RA. So, you can adjust the value of IA to a required value, whatever the armature winding gauge capability is, for a very short time by adjusting the EP value, which means this voltage, and adjusting the RP value, which is this resistance. This can be used to design the armature current value during plugging. Okay. Now, this can bring the motor to a very quick stop. So, to get a relative idea of, let us say, the speed omega and let us say the time t, and let us the speed is here at 1 per unit. This is, let us say, per unit value. This is 1 rated speed. So, when we are coasting, this is going to slow down gradually by its own internal bearing friction, windage loss and things like that one. So, this can take quite a pretty long time to come to 0. So, this is coasting. Mechanical braking, dynamic braking are similar, only that in the mechanical braking you are applying mechanical brake by applying friction onto the shaft by means of brake shoes. That is, you are creating a mechanical friction where the heat is lost as heat in the due to the friction. Now, in the case of dynamic braking, instead of applying on the mechanical side lossy element, we are applying the lossy element on the electrical side by putting a resistor, and the braking effect can be something like that one with a time constant. So, this would be dynamic braking or mechanical braking. Then the third one would be the plugging, and that would be very fast, and you should see that it comes to 0, and then after it comes to 0, because you are applying EP in the reverse direction, it will try to change direct polarity and start rotating reverse direction, but you have to switch off at the point when omega becomes 0. So, this would be plugging. So, plugging would be the fastest. You can control its speed, the rate of decay of the speed by controlling the value of EP or the value of RP. Dynamic braking is putting a resistor across the terminals of the armature, and you can control the speed of decay by controlling the value of the resistor R, which is being put across the terminals, RB. And in the case of the coasting, it is slowest. There is no control on that except that it keeps it will go to 0 due to the energy which is lost in the bearing frictions, windage and things like that one. So, that can take quite a long time if the inertia is very high, load inertia is very high. So, that is about the braking. So, now finally, we would like to discuss about the state space model of the induction motor. It is very simple, just like in the case of the generator. So, we have the motor, we have RA. Now, I am going to include the dynamic element LA, which is going to cause the decay up rise time, fall time of the motor. So, the LA is going to come into the picture, which is nothing but the armature winding reactance, and we have the mechanical shaft. So, here we have the TG and omega, there is reflected inertia, we have the back EMF EB and the input EA. Now, to get the state space model, what you have to do, I have to express it only as EA. There is an IA which is flowing in IA and another state variable omega, just like in the case of a DC generator. So, we have the equations here. So, if we take this loop, EA is equal to IA RA plus L A D IA by dt plus EB is one equation. The other equation is TG will be equal to J d omega by dt plus friction into omega, same as in the case of the DC generator, and this will be K into phi into omega. So, this is also expressible in terms of state variables and input variables. Use these two equations to obtain the state equations. We stop here for the DC motor and continue in the next class. Thank you.